Hello and welcome back to Friday night Year 9 Mathematics. The topic for today is the area of composite shapes. What are composite shapes? Well, they're just shapes that comprise of a number of simpler shapes. So, in fact, the text I think described it as a combination of more simplistic shapes such as triangles and rectangles. So I've got two examples of composite shapes on the board here that we are going to find the area of. Isn't that great? Yay, whiteboard eraser! Right, so this one here is a combination of two shapes. Can you pick the two shapes? If I drew a line about here, I'm pretty sure you would all be able to pick the shapes. There is a rectangle there and half of a circle. So to get the combined area, we work out the area of this surface plus this surface. You just need to add the more primitive shapes together to get the total area. So the area here is going to be a rectangle plus half a circle. So from there we need to remember the formulas. Who remembers the formulas? So for a rectangle, the formula is length width. And what's the area of a circle? Hopefully remember it's pi r squared. So the second bit is going to be 1/2 pi r squared. Once we've written that out, we can simply put the values in. Yay! So it's going to be length 8 times width of 5 plus 1/2 times pi times, oh, bit of a trick. What's the radius going to be? That distance all the way across there is 5. And remember I had the half in there because it's half of a circle, right? But the whole distance across there is 5. That's actually the diameter. We need the radius. So if that's the diameter, the radius is going to be half of that, isn't it? So the radius should be 2.5, 2.5. So that will be 2.5 squared. And now we put that in our calculator. So it's going to be 8 times 5 plus 1/2 times pi times 2.5 squared. Whoops, I didn't put that in right. 8 times 5 plus 0.5 times pi times 2.5 squared. So it looks a bit like that. Equals, and there we go. And because it's got a pi, it's approximating now. So you should use the approximately equal to. And I've got 49.82 metres squared. Ah, baby bumped me at the last second there. You want more pens, baby? There you go. All right. So that's our first example. Just going to check that made sense, given I've got a couple of distractions here. 1/2 times pi times the radius square. Yep, that all works. Rectangle plus half a circle. Looks good to me. Now, what about this thing here? It's an ice cream cone of sorts. Can you see what two primitive objects are involved in this one? Hopefully you can see it if you drew a line across there. This time I've got a triangle and half of a circle. So the area this time is going to be the triangle plus half of a circle. So for that, you'll have to remember the formula for a triangle. 1/2 base height, and again, 1/2 of the area of a circle. Gives us that. Cool? What do you think, Bob? Is that great? Look, calculator. Okay, go back to pens. So, what else have we got there? All right, let's put the values in. Now, you'll notice I have actually made this one relatively easy. I've given you the perpendicular height. Remember for triangles that you need the perpendicular height, so you'd need the height going down here at right angles to the base. All right, I've given you the correct dimensions, which makes this one a little bit easier. So 1/2 times the base, which is 4.9, we're looking at the triangle here, times the height of 10.5, plus 1/2 times pi times, again, I've given you the diameter there, so the radius will be half of that, Half of that's 2.45, so I'm just going to put in that 2.45 squared. We put that in our calculator, so it's 0.5 times 4.9 times 10.5 plus 0.5 times pi times 2.45 squared. So we put that in our calculator, we press equals. Again, we're going to be rounding, so I'm going to use the approximately equal sign. 35.15 centimetres squared. So there we go, we found the area of the ice cream. Oh no, you've only got one left now. All right, so look, that's pretty well all the content for today. It's about splitting pictures of strange objects into their separate parts, finding the area separately and adding them together. And that's pretty well it for this unit, this particular topic. But I'm going to do something weird as purely extension, baby permitting. I'm going to do something that I just thought of earlier, and that is I'm going to tie together Pythagoras, which you were introduced to last year. And what we're going to try and do is find a rule. This is purely extension. You do not have to do this or follow this right now, all right? Rule for area of a regular hexagon. So a regular hexagon is a six-sided object. Looks a bit like this. Now, if I draw the lines... Oi, I need that blue one. Here you go, have a black one. Yeah, it's your lucky one. You got a black one now. All right, if I draw lines here, and I call the length of each side L, how can I find an expression for the area of the whole thing? So I'm going to do this using what we've done so far in mathematics. There's actually other ways of doing it that we can actually advance this in year 10. If you do year 10 methods, you can come up with a better formula that actually happens if you Google it. But right now, each of these, there's 360 degrees in a circle. So how many degrees has to be in each bit? 360 divided by 6 makes it 60. They have to be the same length. They're coming from the centre, right? In effect, what you've got is equilateral triangles in each point. Right? It's 60 degrees, each one of them. Oh, is this not to your satisfaction? Here, you want to have a water bottle? Yeah, water bottle. Right? So... So if we look a little bit closer at each one of these, it's a triangle, but to find the area of a triangle using the rule we've got, remember the area is 1/2 base times height. Now, it's all fine and well that we have the length here, we have length here, we have length here, but to find the area, we need base times height. We actually need this perpendicular height here. Now, you can actually use Pythagoras to get an expression for that perpendicular height. Let's call it h. Right. So this here is h. Does that show up? Oh no, there's a bit of glare there, isn't there? How do I get... Oh, that gets a lot less glare. I might try that way. All right. So if I call that h there, I need an expression for h. Pythagoras was the rule that if you have two sides of a right-angled triangle, you can find the third length. So that rule looked like this. C squared is a squared plus b squared. And from there, we actually want to find out one of the shorter sides. So you have to rearrange this formula because you don't... Remember how C is the hypotenuse? C is the longest side. That's not what we want here. We want one of the shorter sides. To get a squared by itself, I can subtract b squared from both sides. I'm going to swap sides here as well. So that gives me a squared is c squared subtract b squared. To get an expression for just a, the opposite of squaring is a square root. So you get a is the square root of c squared take b squared. Now in our particular situation, we're after this side h. So h is going to be the square root of the hypotenuse squared, so L squared, subtract. Now remember we're actually only looking at this triangle here. Right? We're looking at this right angle triangle. Remember Pythagoras can only be used on right angle triangles. So the three sides of our right angle triangle are this, this and this. The length here isn't L, it's actually L divided by 2. So we get L divided by 2 squared. I can expand that out if we want, square the top and bottom. The length of h there will be L squared subtract L squared over 4. L times L is L squared, 2 squared is 4. Right? That actually gives us a general expression for the height. So therefore, back to our triangle, when we wanted to know the area of this triangle, it's going to be 1/2 times the base, L, times this ridiculous looking expression for h. In fact, you know what? I can now see a way I could simplify this. And I'm going to take this even further. As I said, strictly extension stuff here. Please do not be freaked out. All right. I can see here that I could write that. If I multiply, see this here, it's the same as L squared over 1. If I multiply the top and bottom, I could write it as this. 4L squared over 4. See, if you cancel the 4's, you'd be left with just L squared. So I can actually write it that way. From here, remember how with fractions, to combine them, you need the same denominator? So I have 4 lots of L squared. They're both over 4, so I can combine them. 4 lots of L squared, take away 1 lot of L squared, will give me 3 lots of L squared over 4. Really getting fancy now. You can apply that square root separately to each piece. So it's the same as 1/2 L times root 3 times L times 1/2. Right? If I take the square root of 3, I can't do that, so I've just written it as root 3. If I take the square root of L squared, I get L. If I take the square root of 1/4, I'll get 1/2. If I clean all that up, 1/2 times 1/2 is 1/4. I put the root 3 on top. I'll get root 3 on 4 times L squared. Wow, I hope that I just did that right. Area of, because that's area of a hexagon. I've lost something somewhere in the mix here. No, I actually haven't lost something in here. Remember that that area is for one of only 6 triangles. So if I do 6 triangles at once, so that's only for one triangle. Therefore, the area of 6 triangles is going to be 6 times that. So it'll be 6 times root 3 on 4 L squared. 6 over 4 as a fraction. If you simplify 6 over 4 as a fraction, you get 3 halves, giving a final formula of 3 over 3 root 3 L squared. So I'm going to write that a bit clearer somewhere else. I found a general rule for the area of a hexagon is 3 root 3 over 2 L squared, where L is the length, one of the side lengths in the hexagon. This is actually what you'll get if you Google it. They'll tell you that that exact expression, except they used A there, is the area of a hexagon. How cool is that? So for example, if the length of one side here was 7 centimetres, you could put it in this formula, 3 root 3 over 2 times 7 squared. We put that in our calculator. So 3 times root 3 divided by 2 times, 49. And you'll get an area of approximately 127.31 centimetres squared. Right, that was ridiculous, unnecessary extension activity done purely for the fun of mathematics. That would be fairly intimidating to Year 10 method students, so please don't be too scared off by that. All we really had to do for this lesson was calculate the area of composite shapes. If you've got a square and a triangle, you split it into two parts, find the area of both, add it together, and I just felt that was a little bit easy for you guys, so I hope you enjoyed that. Bye.